warm greetings to everyone. Myself Dr.A. Mydeen Bibi, Assistant Professor of Mathematics, the Standard 5X Rajaratnam College for Women. Today in this session we are going to see about metric spaces. The learning objectives of metric spaces: define and understand the concept of a metric spaces, explain the key components of a metric, a set and a distance function, explore the differences and similarities between various metric spaces through lot of examples we are going to see in this session. Definition of a metric space. First of all, I want to define the metric space. We can define in a metric space in two kinds. First one is set of points and the next one is distance function. A metric space is a set of points where the distance between any two points can be measured. In the distance function, a metric is a function d that assigns a non-negative real number to every pair of points in X satisfying certain properties. The metric properties are positive definite, symmetric and satisfies the triangle inequality. Next, I want to give the metric space a formal definition. A metric space is an ordered pair M, D where M is a set and D is a metric on M, that is D from M cross M to R. First of all, I want to give the four conditions that satisfies the metric space. The first one is it can't be negative, and the second one is all the elements are unique. The distance between any two points is always positive, that is it can't be negative. And the next one is all the elements are unique, that is if d of x comma y equal to 0, if and only if x equal to 0. And the third one is the distance is independent of direction, that is symmetry. The distance from x to y is always the same as the distance from y to x. And the fourth condition, it satisfies the triangle inequality. And we are going to give the examples of various metric spaces. I want to define various metric spaces in this session, that is real numbers, Euclidean spaces, discrete metric spaces, infinite sequences. Real numbers. The most familiar example with the standard distance function is modulus of x minus y. In this session we are going to see deeply about that. Euclidean spaces. N dimensional spaces with the Euclidean distance d of x comma y equal to summation root of modulus of x minus xi minus yi the whole square. In the discrete metric spaces, any set x with the distinct metric which is equal to 0 if x equal to y and 1 otherwise. In the infinite sequences, the space of infinite sequences with supremum metric d of x comma y, which is supremum of modulus of x comma y. We are going to check about the least upper bound, supremum and all in this session. Examples of metric spaces in real, that is in R. In R, we are going to prove that d is a metric on R. Always this is called as usual metric on R. If we satisfies the four properties of metric space, we need to prove that first one is non-negative, and the second one is all the elements are unique, and the third one is symmetric, and the fourth one is it holds the triangle inequality. For the non-negative, we need to prove the metric space that we are taking d of x comma y equal to modulus of x minus y, which is greater than or equal to 0. And the next one is all the elements are unique. If we are taking d of x comma y equal to 0, if and only if x equal to y. And the third one is symmetric, that is the distance between the two vectors on that set. D of x comma y equal to d of y comma x. And the third one is triangle inequality. If we satisfies the four conditions, then it is metric on R. The next one is example of metric space in complex numbers in C. In C, we define d of z comma w equal to modulus of z comma w, that is minus w. It satisfies the four properties of metric space, then it is a metric on C. And we call this as usual metric on C. If the complex number z is equal to x plus iy, we are identified with the points xy of the two-dimensional Euclidean plane, then the above distance formula takes the form, that is d of z comma w, the metric d of z comma w equal to root of x minus u the whole square plus y minus v the whole square. This is nothing but the usual distance between the points xy and uv in the plane. The next we are going to see about example of metric space in distinct metric, that is discrete metric. Already we mentioned that real numbers metric space, the examples of metric space in real numbers, Euclidean space, discrete metric, and then infinite sequences. In discrete metric we are going to see now. On any non-empty set M, we define D as D of x comma y equal to 0 if x equal to y, 1 if x not equal to y. If we prove that D is a metric on M, this is called the discrete metric on M. Here also we are going to prove the metric with 4 conditions, that is D of x comma y is greater than or equal to 0, D of x comma y equal to 0 if and only if x equal to y, and also the symmetry property and triangle inequality. We are proving the triangle inequality in 2 cases because we are having 0 if x equal to y and 1 if x not equal to y. We are creating 2 cases, that is x equal to z and x not equal to z for the triangle inequality. Both the cases it satisfies the triangle inequality, so therefore hence D is a metric on M. And the next one, that is an example of metric space, that is usual metric. In R power n, we define already Euclidean spaces. So R power n with usual metric is called the n dimensional Euclidean space. In R power n, D of x comma y can be defined like this, where x is equal to x1, x2 and so on n spaces, and y equal to y1, y2 and so on n spaces. Then D is a metric on R power n. If satisfies the 4 properties, then it is a metric on R power n. This is called the usual metric on R. We are going to prove the 4 conditions of the metric spaces, and the first one is non-negative, second one is usual, all the elements are unique, and the third one is symmetric, and the fourth one is triangle inequality. It satisfies the non-negative condition and it is unique if D of x comma y equal to 0 if and only if x equal to y. D of x comma y equal to D of y comma x. It also satisfies the symmetric condition too, and also it satisfies the triangle inequality. Therefore, D is a metric on R power n too. And the next one, we are going to define that example of metric space in LP, that is an infinite sequence we are going to see. Check out. Also, we are going to check the set of all sequences xn, right? So, we are taking P greater than or equal to 1. I am going to prove that D is a metric on LP. LP denote what is LP? LP denote the set of all sequence xn such that summation modulus of xn power p is convergent. So, here we need to prove the metric on LP. First we need to prove the convergent sequence. If it is convergent or not, we need to check. So, I am going to prove that D of a comma b is a real number. I am taking D of a comma b is a real number. Then I am going to prove the convergent series. So, by use of Minkowski's inequality, I am going to prove the right hand side of the limit, that is which converges to converges the finite limit as n tends to infinity. So, we proved that it is a convergent series. Similarly, we can prove the left hand side is also a convergent series, and hence D of a comma b is a real number. If we prove that D of a comma b is a real number, then we can easily prove that D is a metric on L power LP, which satisfies the 4 conditions. The first one is non-negative, and the second one is unique, and the fourth one is, the third one is symmetric, and the fourth one is triangle inequality holds, which satisfies the 4 conditions, and it is a metric on LP. Finally, we are going to check that L infinite sequence, examples of metric space. And before that, I am going to prove the supremum power also. Let M be the set of all bounded real value functions defined on a non-empty set E, defining D of f comma g as a supremum of modulus of f of x minus g of x. Then D is a metric on M. We need to satisfy the 4 conditions to prove it is a metric on M. So, first one is non-negative, and the second one is unique. Every element is unique, and the third one is symmetric, and the fourth one is triangle inequality. Here I proved 4 conditions that D is a metric on M. Finally, we are moving to the infinite sequence, that is L infinity. Example of metric space in L infinity. First I define L infinity. Let L infinity denote the set of all bounded sequence of real numbers, infinite sequence. I am taking let x equal to xn and y equal to yn belongs to L infinity space. I am defining the metric D of x comma y equal to least upper bound of modulus of xn minus yn. I am going to prove that D is a metric on L infinity. So, I need to prove the 4 conditions of a metric space, that is D of x comma y is greater than or equal to 0, and it is unique, that is D of x comma y equal to 0 if and only if x equal to y, and the third one is it is symmetry, that is D of x comma y equal to D of y comma x, and the fourth one is triangle inequality. And here I prove that D is a metric on L infinity. I hope you all enjoyed this session. and also you know about the metric space, what we did, the definition and the various examples of metric spaces in real numbers and Euclidean space and discrete metric and infinite sequence. We will meet in the next video. Thanks so much.